if I talk to you about a limit, that's what the graph height looks like it's going to be. You might want to make a note of that to yourself too. So when we say limits, I mean what height am I going to? What function value? Okay. The x value is going to be the limit as x tends to something. As x is going towards something, what does it look like your graph's height is going to be? The important thing with a limit is it doesn't actually matter what your graph's height actually is. Okay, we'll get to that in a minute. Before we get to all of that and do some examples, let me talk to you about some notation. Okay, so if I have a graph of f of x, or a function f of x, and I want to say that, here's a graph. Here's the x value. Let's say that that's the target x value. So I'm actually going to be pointing toward that x value on the x-axis. And I'm going to go from both directions for right now. Okay, so as my graph goes toward that x value, what is my graph actually doing? So what is the graph traveling toward? Okay, so that point right there is actually on your graph, in this case, most likely, but we have to zoom in a lot on our graphing calculator or on a graph to actually see that. We don't know if it's a hole or not, okay? However, what height your graph looks like it's tending toward is the limit, okay? Here's some notation to help you. LIM is the abbreviation for limit, okay? And you say the limit as x goes towards some value, okay, which we'll say c. So I'm going to change my graph back to c right there. The limit as x tends to some value c of some function is equal to whatever the limit is equal to. And you should get a number for the limit. All right, most likely. And it should be the height that your graph looks like it's going toward at that x value of c. So as the graph goes toward the x value of c, what's the height of your graph pointing at? Okay. This is the notation. And it's read, the limit as x tends to c of f of x equals L. Maybe you should write that down in quotes, all right? The limit as x tends to c of f of x equals L. Okay? So here's an example. The limit as x tends to 3 of 5x plus 3. We're going to evaluate this limit numerically, graphically, and algebraically. We're going to evaluate it algebraically last, okay? And that's probably the one that's going to be easiest, but it won't always work. So you need graphically and numerically in your tool bag as well. All right, so let's look at this thing graphically first. So we want to know, what does the limit as x tends to 3 of 5x plus 3 equal? So if I'm going to graph this, I graph the line y equals 5x plus 3. How do I graph the line y equals 5x plus 3? And there will be times where you're given a graph and asked to evaluate, and it's easy to do because you just look, but you have to know what you're looking for. Huh? You can make a table. We're going to do that in a minute numerically to evaluate it anyway. But you don't need to make a table for graphing this, which is a, it's probably faster to do slope-intercept form. Okay, this is slope-intercept form, so y equals mx plus b. What do I do to graph this?
Start at 3.
Start at 3 on the y-axis. Very good. And then what?
Go up 5 and to the right 1.
Okay, and then to get to another point, you're going to go up 5 and right 1. Try to graph as straight as possible. Obviously, you have Desmos and you have graphing utilities and things on your tablets. And next year you'll have graphing calculators, okay? Some of you may have a graphing calculator now. So I want to know what's the limit as x tends to 3 of this graph. So what I need to do, this is the x value of 1, the x value of 3 is right here, okay? As x is going to 3 from both sides, what's my graph doing? That's what I need to analyze, okay? So my x value of 3 what height does that look like it's going toward? Now, if you had a graphing calculator, it'd be probably a little bit easier than it is on the board, because on the board it's approximated, okay? But basically, I could continue my slope. You're saying 18. I probably agree with that, because you have to go 5 units above 3 to get to 1, and you have to go another 5 units above 3 to get to 2, and you have to go another 5 units above 3 to get to 3. So you have to go 15 units above 3 to get to the x value of 3, which takes me to y equals 18. So I think this thing is equal to 18. But let's figure it out numerically just to be sure, and then we'll do algebraically, which is the one I think you'll probably like the best. Okay, if possible, algebraically is probably going to be easiest. So let's do with a table. So this is graphically. Graphically probably is the best way if you're given the graph. If you're not given the graph, it might be easier to do one of the other two ways. Numerically basically means to use a table, but you have to know what to put in your table. Here's what you're going to do. You're trying to make your x values go toward the limit value of 3, and you're trying to see what your y values approach. Okay, so you're going to plug in x values on both sides of 3. All right. So what numbers are on both sides of 3? Let's see. Maybe, and it might help to pick some that are pretty close to 3. So like, I don't know, 2 and 2.5. That might be enough. I might want one more. Okay, I can probably tell what it's going to do with a couple of them. On the right side of 3, I might pick like 4 and 3.5. Okay. Remember, you're not actually interested in what your graph actually approaches, although that would tell you the limit if you can figure it out. It doesn't matter if it's the same thing. It doesn't have to actually exist at that point. Okay, so plug in the x value of 2 to your function. Y equals 5x plus 3. So 2 plugged in is going to give me what? 13. If I plug in 2.5, what do I get? What's 5 times 2.5? Plus 3. Huh? 15.5. I might want one more value. 3.5 gives me what? If I plug in 3.5 to 5x plus 3, I'm going to get
20.5.
20.5. Okay, how about 4? If you plug in 4, what do you get? 23. Okay, so we know that our actual limit value has to be between 15.5 and 20.5. The problem is that we don't really know specifically what it is. We just found the range of possible values. Okay, so maybe I should pick something a little closer to 3. Give me 2 numbers, one on each side, that would be very close to 3. 2.9 and 3.1, or even 2.99 and 3.01. Okay, so let's get a calculator. If I plug in 2.9, let's plug in 2.99 just to prove a point. Okay, so if I extend this table a little bit, if I plug in 2.99 for x, yeah.
Why don't we just plug in 3?
Yeah, why don't we just plug in 3? That's called evaluating algebraically. And the answer is because you won't always be able to plug the x value into your limit. Maybe your function is undefined at that x value momentarily, but it exists everywhere else. Okay, like I said, your function value doesn't have to actually equal your limit. So evaluating numerically is probably one of those things where you'll you'll use it if you're given a table and not the function. Okay, so if you're given a table of values and asked to evaluate the limit, you can do that with evaluating numerically. You have to know what you're looking for. Okay, or if your graph or your function doesn't exist at that value, you may choose to evaluate numerically. So this is an example of one where it works all 3 ways. Huh? I'm talking about a graph that has like a hole in it. We'll get to that. Okay, so a graph like this. Maybe you just jump over that value momentarily. Your graph is not defined at that value, like 1 over x. Well, 1 over x is not a hole. It has an x squared minus 2x all over x minus 2. That has a hole at x equals 2. Okay, so that type of a graph, you can't just plug a value in. All right, direct substitution does not work, is what that's called. We'll get to that. In this case, you can just plug in 3, and we're going to do that in a minute. Okay, so if I plug in 2.99, I get 5 times 2.99, and then I have to add 3 to that, and I get 17.95. Then if I plug in 3.01, what do I get? Let's see, 5 times 3.01 plus 3 is going to give me 18.05. What does it look like your graph is approaching? What height? What y value? 18. And we decided that before, too. Okay, and 18 fits the bill. It's between 15.5 and 20.5. All right, but more specifically, it's between 17.95 and 18.05.
If you take like the 2 numbers that are closest to it, rather you take 2.99, 3.01, like you average it, it gives you.
Okay, that's true because this is a line. If you're dealing with a curve, it won't be exactly true. It'll still be close, but it won't always be exactly halfway between the y values, even if it's halfway between the x values, because the vertical change is not always constant. Any curve, the change is changing. The slope is changing. Does that make sense? Ariel.
So numerically, do you know
Least used or least exact? I think graphically actually is probably the least exact. Numerically, you're at least coming up with values that are numbers. You know, you're not looking at it and
But if you
approximating.
did it to like that and you didn't have any other way to do it besides numerically, then how do you know for sure that you have to get?
You're estimating. Yep. So graphically, numerically, now the one Austin's been waiting for, algebraically. Yep. To evaluate a limit algebraically, it's pretty straightforward, unless you have to do some tinkering around with the function to get it to work. Okay? To evaluate a limit algebraically, you want to try to plug the x value in for x and evaluate. Okay? You want to get to a point where you can plug x in. So for this problem, we can do that very quickly. Take 5 times the x value of 3 and then add 3. 15 plus 3 gives me 18 for my limit. So we came up with the limit value 3 different ways. Sometimes you'll only be able to do one of these. Okay? Algebraically is probably the most exact if it works, but the problem is that it won't always be possible to do. Okay? When won't it? If your graph is undefined at that value. and it's not removable. So like 1 over x. If you were trying to take the limit as x tends to 0 of 1 over x, you can't just plug 0 into that y. That's right. You can't divide by 0. You can't have a fraction with 0 in the denominator. It doesn't work. Dividing by 0 is undefined. So you cannot just straightforward plug in 0. You need to use a table of values or a graph, probably a table of values. Okay. Okay. And on that note, by the way, limits can approach a height of infinite values. So it could equal infinity or negative infinity if it's going infinitely low. Okay, we'll get to that later. That's not even today. Okay, so first example, evaluating limits graphically, numerically, and algebraically. Okay. Can I erase that? May I erase that? All right. Limits are what it looks like the graph is approaching. Sometimes it helps people if I describe it as like one of the roller coasters at Cedar Point. If it were to be traveling on the coaster, and I would never recommend this, but let's say that one of the tracks is missing a screw. Okay. But if it is, granted, it's probably going to be fixed, but is it going to stop where the coaster goes? Probably not. Okay, the coaster will probably still travel over that height. So even if you have a little hole in your graph, your limit value hasn't changed. Your function value is undefined. There's still a hole, but the limit value hasn't changed. Okay? All right, let's try this one. I'm going to give you a table this time. Okay, so let's say that I have the table with x and f of x. And let's say my table x values are negative 0.01, negative 0.001, negative 0.0001, .001, 0.001, and 0.01. Okay. Let's say that my function values that go with those are 5.998, 5.99998, 5.99998. Okay? You get the idea of what's happening? 5.99998 again. 5.9998 and 5.998. Okay? First of all, I didn't give you a limit problem for this one. I just gave you the table. So let's say that I want to use this table. I'm not going to make you come up with the limit expression this time. Okay, I may do that someday, but not right now. So let's say that I want to ask you to use this table to find the limit as x tends to 0 of f of x. Use that table to numerically evaluate what the limit as x tends to 0 of f of x is equal to. Okay? So first of all, the x value of 0, I need to approach the x value of 0 from both directions. The x value of 0 happens to be right here. Would anyone like to give me the answer to this limit? Yeah. 6. How'd you get that?
As it approaches 0 from both sides,
the y value seems to be heading towards 6, doesn't it? As the x value approaches 0 from both directions. I agree. So the y value is heading to 6 from both sides. So my limit value is 6. Let's do that. Okay. Again, the limit is the y value that it looks like your function is heading toward. from both directions unless otherwise specified. We can do limits from one side. We'll get to those later. Okay? By the way, this function, I didn't tell you this, but this function is x over the square root of x plus 9 minus 3. This function is x over the square root of x plus 9 minus 3. Okay? But I did all the y values and x values for you. I gave you the table. You don't actually need the function itself in order to come up with the limit value if you're given a table or graph. Okay? Now, let me ask you a question. Since I gave you the equation now, is it possible to just plug 0 in right here for x and evaluate? My actual function is f of x equals x over the square root of x plus 9 minus 3. Just writing it bigger in case you can't see that.
No.
Is it possible to evaluate f of 0? You're saying no. Why?
Because you get 0 for the denominator.
Okay, you get 0 on the top, but you also get the square root of 9 minus 3, and the square root of 9 is 3. Then I subtract 3 from that, and I get 0 over 0. Ladies and gentlemen, that's what we call indeterminate form. Okay, when you have a fraction that involves a 0 at an infinity, or negative infinity, it's called indeterminate form. It means you can't determine what that equals. It's not that it doesn't exist, you just don't know what it equals. The limit exists, the function value doesn't.
Give us a problem where we can say that.
What, where the limit does not exist? We'll get there, but it's probably not going to be there. What? Okay. You want an example where a limit does not exist?
Well, don't
I'll give
tell
you
us it doesn't exist.
Okay.
No.
So let me ask you this. May I erase this one?
Yes.
Let me do one with you graphically, since we did one that works algebraically, and now we've done one that we can only really do numerically, okay, because I gave you the table, or it's easiest numerically, I should say. Now let's do one where graphically is probably easiest. Okay, on this graph, that's x, that's y, and this graph, all piecewise graph, is f of x. Okay? Now, this is the x value of 2, 1. This is the y value of 1, 2, and 3. All right? So I want you to try to use this graph to evaluate the limit as x approaches 2 of f of x. What would the limit as x approaches 2 of this function equal? So on your graph, you need to look at what the function heights are approaching. Okay, so as your x values go toward 2 from both sides, what's your function height doing? Let me do that again. As your x value approaches 2 from both sides, what's your function height approaching? Not 2, 3, but this side's not approaching 3.
It remains constant.
Yeah, the y value remains constant on each side of 2.
Yeah, yeah.
But what does it do locally close to 2 from both sides? How would you, it switches. It switches. It does not approach the same value from each side. Okay, it does not look like these values are going toward the same height at all. So the heights are different. So therefore the limit does not exist.
Wait.
Oh,
Wait,
go ahead.
what? Wait, what?
Sorry. What is it?
The limit does not exist.
Oh, yeah.
There we go.
Okay, now you can write does not exist. You can also abbreviate it D, N, E. I'm fine with that. All right, but the limit does not exist if your function heights approach two different things from each side. If it approaches one thing from the left and something else from the right, your two-sided limit does not exist. Okay, there you go.
I'm going to show you that clip.
Let me give you one where the limit might exist graphically. Let's do another one graphically, just so that you don't think, oh, if I'm solving it, if I'm given a graph, it can't exist. No, no, no. Might exist. All right. How about this one? Let's do some more straight lines. That's an open circle, in case you're wondering. And let's say that that's the y value of 1, which makes that the y value of 2. Okay, and this is 1, 2, and 3. So I want you to, and this is the graph of f of x. I should have put that over here too. So let's say that I want to use this graph to evaluate the limit as x approaches 3 of f of x. Evaluate the limit. What does the limit as x approaches 3 of f of x equal? So here we go. As your x values approach 3 from both sides, what does your function height do? It approaches what? 2. It approaches 2. Look at that. As your x value goes toward 3, your y value is approaching the height of 2. In fact, it was 2 all the way along. Now, is the function height actually 2? Is f of 3 equal to 2?
No.
Think about it. I'm not saying you're wrong. I'm just saying the graph tells me enough information to know. In this case, does f of 3 equal to? Is the function height at 3 equal to 2? Why are you saying no, and why are you saying no? We'll go that way.
Well, f of 3 would actually equal 2, but that was the function.
How do you know f of 3 doesn't equal 2? There's an open circle. The function is only existing where there's dark colored in lines and things. It doesn't exist if you have an open circle. If you have an empty space, the function is not there. So no, at that spot the function doesn't exist. The limit exists, the function doesn't. Remember, the limit is what the graph looks like it's approaching. It's not actually always the same as what the function actually is. Does that make sense? It's like if you were standing here and looking ahead, what does it look like your height is going to be? Okay, that's what the limit is asking. The limit is not actually asking you to stand there, what are you on?